Uh, Good morning, everyone. My name is Pramit Banerjee, and today I am going to present my project titled Home Automation System, which I developed during my internship at Emertxe. Throughout this presentation, I will walk you through what I learned during the internship, the technologies involved, and finally how I implemented my project using Arduino, IoT, and simulation tools. Uh, Here is an overview of what I will be covering today. First, I will discuss the key concepts I learned, including C programming, pointers, C++, embedded systems, IoT. Next, and then I will explain my project, the home automation system. Its architecture, development tools, functional modules, and implementation steps are also included. Finally, I will summarize the outcomes and give a short demonstration using the simulator. Let's begin with the foundation C programming. C programming forms the foundation of all embedded system development. During this internship, I strengthened my understanding of data types, number systems, and data representation, which are crucial for memory efficiency in microcontrollers. I learned about operators, arithmetic, logical, relational, and bitwise, which help in efficient bit level control. I practiced control structures like if-else, switch case, and loops to create decision-based and repetitive logic. Functions were introduced for modular programming, making the code reusable and organized. I also explored storage classes like auto, static, extern, and register, understanding how variables behave across functions and files. A major takeaway was the understanding of memory segments, the stack, heap, data, and BSS, which helped me optimize code for low memory embedded environments. This learning became the stepping stone for embedded programming using Arduino. Let's move to the next slide. Pointers and arrays. These are the core of efficient embedded programming. I learned how pointers allow direct access to memory addresses, which are crucial when dealing with sensors, actuators, and hardware registers. I explored pointer arithmetic and how arrays can be used for storing sensors readings or control data efficiently. Understanding call by reference improved my grasp on data handling between functions. This knowledge became very useful in managing hardware input-output since most Arduino functions use pointers internally. By understanding how memory is allocated and accessed, I was able to write optimized, stable embedded code. Let's move towards next. After mastering C, I learned the basic of C++ and object-oriented programming, which introduced structure and modularity to my coding. Concepts like classes, objects, inheritance, and encapsulation taught me how to organize code into logical components such as sensors, actuators, and communication interfaces. This also helped me understanding how modern IoT frameworks like Blynk use objects and APIs to manage devices and data seamlessly. In short, C++ enhanced my ability to think in terms of reusable and scalable code blocks, which is essential in embedded and IoT development. Next, embedded systems. Moving ahead to embedded systems, I learned that an embedded system is a combination of hardware and software designed for a specific function. Examples we include home appliances, cars, industrial machines, and medical equipments. Each embedded system consists of a processor, sensors, actuators, memory, and software control. I also learned that embedded systems can be classified as standalone, real-time networked or mobile. Understanding how hardware and software interact gave me the base to design my own embedded application, the home automation system. Embedded systems are everywhere in televisions, washing machines, automotive controls, and even IoT devices. They are designed for efficiency, reliability, and continuous operation. Through simulation labs, I practiced in microcontrollers like Atmega 328P, understanding GPIO pins and peripheral interfacings such as ADC, PWM, and serial communication. These experiments helped me realize how embedded systems form the building blocks for IoT applications. The next major area I learned was the Internet of Things or IoT. IoT is about connecting physical devices like sensors, lights, or motors to the internet to exchange data. I learned that IoT enables bidirectional communication between the device and the user. For the example, a user can control home appliances from a mobile app and the devices can send live status updates back to the cloud. IoT combines hardware connectivity and cloud infrastructure, bridging embedded systems with the digital world. Now coming to IoT architecture, IoT architecture typically is of four layers: device layer, gateway layer, cloud or server layer, application layer. Device layer where sensors and actuators collect and execute data. Gateway layer which transfers data to the internet securely. Cloud or server layer where data is stored, processed and analyzed. Application layer which allows users to monitor and control devices through apps or dashboards. I also learned about communication protocols like MQTT and HTTP and how IoT platforms such as Blynk Cloud manage data efficiently using virtual pins. Next, moving towards the project overview. The goal of this project was to control and monitor household devices remotely through the internet. It includes controlling lights, monitoring room temperature, managing a simulated water tank, and automating certain functions based on sensor readings. All these components work together using Arduino, Blynk Cloud, and a simulation environment. Through this project, I could apply every concept I learned from programming to embedded interfacing and IoT communication. Next, development tools interview overview. For development, I used a few essential tools like Arduino IDE, which I used for writing and uploading the embedded C and C++ code. PICSimLab, a simulation tool that replicates Arduino hardware and allows testing of the code virtually. Virtual serial port emulator or virtual serial port tool to create serial connections between the Arduino and the simulated tank. Blynk IoT apps and web consoles to monitor and control devices remotely via cloud communication. These tools allowed me to design, test, and debug the entire system without physical hardware. Now, coming to home automation system architecture. The home automation system is consists of several key components like Arduino or microcontroller ATmega 328P as the brain of the system, sensors and peripherals like LDR, LM35 temperature sensor, CLCD, LEDs, and serial tank simulator. Also, Blynk Cloud and app for data exchange and user interface. The data flows between sensors, Arduino, and the cloud, allowing the system to make decisions automatically or based on user input. Functional modules. The project is divided into functional modules, each tested individually before integration. These include LED control module, CLCD display module, analog input module for LDR and LM35, PWM module output module, serial communication module for tank simulation, Blynk IoT module. Each module performs a specific task, forming the foundation for the final integrated system. Also, I used several fundamental Arduino functions like pin mode to configure pins as input or output, digital write to set a pin high or low, analog read to read sensor values, analog write to generate PWM signals for brightness or motor control, delay to add time gaps for timing control, serial begin, serial read, and serial write for serial communication. These functions were the build blocks for the project code. The first test was a simple LED blink program used to verify Arduino's output control. I configured pin 13 as output and toggled it on and off every second using digital write and delay. This basic test confirmed that the simulation environment and Arduino were working correctly. Next, I interfaced a character LCD or CLCD using the Liquid Crystal I2C library. By including liquid crystal I2C.H and wire.h, I could initialize the LCD with I2C address 0x27 and display text. This interface displayed informations like temperature, volume, or device status during the project. It was a key part of user feedback in the system. The pulse width modulation. Here I learned about PWM or pulse width modulation, a technique to vary voltage by changing the duty cycle. Using analog write, I gradually increased and decreased the duty cycle to dim and brighten an LED. This experiment helped me understand how PWM can be used for speed or intensity control in embedded systems. Also, we have used this PWM in the actual code in using a loop. 0 is used for to off and 255 to fully on the PWM. In next step is LDR. In this step, I used an LDR to sense ambient light. By reading its analog value using analog read A0, I mapped the sensor input to a PWM output controlling the LED brightness. This created an automatic brightness control system, dimming lights in bright conditions and brightening them in the dark. Next, I interfaced the LM35 temperature sensor. It outputs voltage proportional to temperature, which is 10 millivolt per degree Celsius. Using analog read, I converted the ADC value to voltage, then to temperature in Celsius, and displayed it on the CLCD. This was an important step in monitoring real-time environmental data. Then I worked on serial tank simulation. Here the Arduino communicates with the virtual tank software via serial communication. I controlled actuators like the inlet and outlet valves, heater, cooler, and using serial write commands. Sensor data such as volume and temperature were received using serial read. I also learned synchronization techniques using baud rate 19200 to ensure accurate data exchange. Now, Blynk IoT integration. This was the most interesting part when we integrated the Blynk IoT Cloud with the Arduino. I included Blynk Simple Ethernet.h to connect Arduino via Ethernet to the Blynk Cloud. As we know, our Arduino Uno doesn't support internet, so we have to connect the Ethernet with Arduino using wire. The Blynk app allowed me to control and monitor everything using virtual pins, buttons, and gauges on the app were linked with Arduino logic through functions like Blynk Write and Blynk Virtual Write. For example, if the temperature went above 35 degrees Celsius, the heater automatically turned off, and when the tank volume exceeded 2000 liters, the inlet valve closed automatically. This automation made the project smart and efficient. Finally, I integrated all modules LED, CLCD, sensors, serial tank, and Blynk Cloud into one complete system. The Arduino collected data from sensors, displayed it on CLCD, communicated with the serial tank, and sent live updates to the Blynk Cloud. The Blynk app allowed remote control of lights, bulbs, and heater-cooler systems in real time. This demonstrated how an entire home automation ecosystem can be built using affordable open source tools. Here is how the logic works. Sensors readings from LDR LM35 and the tank are continuously taken. Based on threshold conditions, control actions are triggered automatically. Data is updated to Blynk Cloud using virtual pins. Using inputs from the Blynk app are read and executed by Arduino in real time. This combination of local automation and cloud connectivity represents a true IoT-enabled embedded system. To summarize, during this internship, I learned the full journey from programming basics in C and C++ to embedded systems, IoT, and finally real-world project implementation. I developed a working home automation prototype that performs environmental monitoring and smart control using cloud connectivity. This project enhanced my skills in embedded programming, serial communication, and IoT integration, preparing me for future embedded and IoT-based innovations. Thank you. That brings me to the end of my presentation. Thank you for your time and attention. Thank you, Emertxe, for the opportunity. Now I will proceed to show the live simulation demo where I will explain how each of these modules works together to form the concept of complete home automation system. First, I will be explaining the overview of the simulation and components. After that, I will explain the live simulation. So this is the home interface of PICSimLab. We can see that this is the Arduino Uno board. Here we used the module is ATmega 328P here and which doesn't support internets. That's why we have to connect the Ethernet shield with the ATmega 328P. This green indicator denotes that the Ethernet shield is on and it is connected with the Blynk IoT app or Blynk Cloud. And this yellow light blinking means that the Ethernet shield or the ATmega 328P is connected to the Blynk Cloud or Blynk IoT app through this Ethernet shield. Then there is the LED and LDR sensor. If we increase the LDR to the max position, which means that the light outside is available, the light outside is not available, then the LED will glow. And when we toggle the LED to the zeroth position, then the LED will not glow. That means that when the LDR is at zeroth position, there is no light outside. This is the CLCD where we are displaying the temperature of the home or the temperature of the system, the heater or cooler on or off status, the volume of the cereal tank, and the status of inlet or outlet valve or the inflow or outflow. Now this is the temperature system and this is the fan which is also work as the cooler. Now we will see the cereal tank. This is the cereal tank and this is the serial port, which means that we need to connect the Arduino. We need to connect the Arduino with the serial remote tank with using a serial connection. I have used null emulator here, which serially connects the Arduino with the serial tank. What is the meaning of the serial connection? That the data will be the data will move serially from Arduino to the serial remote tank. Now I will operate different components of Arduino by using Blynk IoT app. Okay, now the Blynk IoT app is already connected, and if we see that now I am turning on the heater, you can see that the status is shown here as heater on, and there is a condition we used that if the room temperature touches 35 degrees Celsius, the heater will automatically turn off. Now if I turn on the cooler, you can see that the status is also shown here as cooler on, and the temperature is also decreasing. Now, now turning on the inlet valve, we can see that the tank is started to fill, but as the tank is full, we can't see any difference. So I will now turn on the outlet valve. We have also used in condition here that if the volume of the tank go below 2000 liters, then the inlet valve will automatically turn on, just like this. When the now again I will be showing the example again. The inlet valve is on now, and the status is also showed as of the outflow or outlet valve. So the status is showing outflow off, and the volume of the tank is increasing. Now I will turn off the inlet valve. The status is also shown here as inflow off. Now again I will turn on the outlet valve, and the volume of the tank is decreasing. The water volume is decreasing, and when it goes below 2000 liters, the inflow will automatically on. That means that the inlet valve will automatically turn on, and the tank starts to filling. So this concludes my presentation. Thank you for watching.